Hi, I'm Professor Goins, and welcome to the Math Professor's YouTube channel. We cover mathematical topics ranging from beginning algebra up through calculus, more advanced topics as well. So if that's what you're looking for, please consider subscribing to our channel and checking out some of our videos. Let's go ahead and start with the current video. What I want to take a look at is the topic of separable differential equations. And a differential equation is separable if it can be written in the following form. Okay. That is, if it can be written in the form where I have the first derivative of the unknown function is equal to an expression that I can write as a product of terms in x multiplied by terms in y. So I can actually factor this expression so that I've got terms in x, terms in y. Now, equivalently, I can write this as follows. Where I can write it as a division, where, of course, g of y is just the reciprocal of h of y, because division is just multiplying by the reciprocal. And the reason that I want to do that is just to make the following notation a little clearer. It really doesn't make a big difference. The idea is that I can write the expression in a product of terms in x and terms in y. Then here's what I'm going to go ahead and do in order to solve this type of an equation. I'm going to multiply both sides by g of y. That would give me the derivative of the unknown function multiplied by an expression of the unknown function is equal to the whatever expression I have using the independent variable x. After I have this expression down here, I'm going to integrate both sides with respect to x. So integral of the left-hand side with respect to x. And then I'm going to integrate the right-hand side with respect to x. And that gives me the following. Now, in order to simplify this, I'm going to use a u substitution. And I'm going to use a u substitution as follows. I'm going to say u is equal to the function y of x. Remember, y is your independent or your dependent variable, x is your dependent variable, and so throughout this differential equation, y is actually a function of x. So therefore, I'll set u to be this unknown function. Then, when I take the differential of this, the differential of u is dy dx, right? It's the derivative of that, and then multiplied by the differential of the variable x. So du is dy dx over dx, and therefore I can take that and I can substitute that back into this integral, and that would give me the integral of g of u, right, because y is u, and dy dx is du, so that's the integral of g of u du, is equal to the integral of f of x dx. Now, within this integral of g, the function g, remember that the u is simply a dummy variable. I can replace it with any letter I like. So I'm going to go ahead and replace it with y, and that gives me the following. Integral of g of x, I'm sorry, g of y dy is equal to the integral of f of x dx. Let's compare that with the original differential equation. What I'm going to do is, symbolically, it looks like I cross multiply and then integrate. Okay, so I have dy times g of y is equal to f of x dx, and then we integrate both sides. Now, throughout the exercises, that's going to be my first step, is to separate the variables, cross multiply, integrate, and then once I get to this step, I'm going to integrate both sides, and then I'm going to have an expression in y and an expression in x. If I can actually solve for y, then I can get an explicit function. If I cannot solve for y, then I could have an implicit function. But that's going to be the general procedure for how we use the technique of separation of variables. Let's take a look at a first example. So let's look at the differential equation dy dx is equal to, let's say, x squared y. Okay. Notice that that does have the form that we started with over here that I initially mentioned. I've got a derivative. The unknown function is equal to an expression in the independent variable x multiplied by the an expression in the unknown function. So I've got x squared times y. Well, again, what we do is we separate all the y terms on the left, all the x terms on the right, and therefore I would get dy over y is equal to x squared dx. And then we integrate both sides. Okay. Integrating the left-hand side, we get the natural log of y, and in fact it's the natural log of the absolute value of y, just in case y happened to be negative, is equal to x cubed over 3, and then there is a constant, of course, of integration, so plus c. And then if I left it as this right here, this would be an implicit solution because I do not have the variable y solved for. And, excuse me, in this particular case, since I don't have any sort of initial conditions, I don't know if y is positive or negative, I'm going to leave it in the form of an implicit solution. If we had more information about the unknown function y at the beginning, you know, we could undo the natural log using the natural exponential function, and then we could get an explicit solution for y in this case. All right, let's take a look at a second example. And I mentioned being able to solve for y as an implicit, going from an implicit solution to an explicit solution, we might need more information about the unknown function, for example, an initial condition. So let's, for our next example, let's go ahead and do an initial value problem. Let's say I've got the derivative of y is equal to xy cubed over the square root of 1 plus x squared, and let's say my initial condition is y of 0 is equal to negative 1. Now I'm going to need more space for this. Let me go ahead and clean this side up first. Now, as I'm erasing this, you can see that that expression is written as a product of terms in x and terms in y. So let's clean this up, and then we'll go ahead and walk through that exercise. All right, here we go. Solution. Again, I can see that the expression is written as a product x divided by the square root of 1 plus x squared, so that's my x expression multiplied by y to the third. I have it written as a single fraction there, but I could just take y cubed and pull it off at the end, and we can see that again it is separated in terms of a product of terms in x and terms in y. So then what we'll do is we will separate the variables by writing all the y terms on one side. That gives me dy over y cubed is equal to x over the square root of 1 plus x squared dx. Again, we separated the variables. From here, I'm going to go ahead and integrate. So then we're going to integrate the left side and the right side. And to integrate the left-hand side, remember that 1 over y cubed is the same thing as y to the negative third. So go ahead and write that in a more appropriate format as far as just being able to think through the integration. On the right-hand side, notice that this is applicable for a u substitution. So what I can do is let's go ahead and write out what my u substitution would be. Notice that the inside function of the radical, its derivative up to a constant factor, right, appears as a factor of the integrand. So therefore u is going to be 1 plus x squared. That means du would be 2x dx. That factor of 2 is missing, or said differently, I can write x dx as 1/2 du. So therefore the x and the dx will get replaced with 1/2 du. And let's see what else we can do with that. When I plug that in, well, let's just go ahead and substitute everything in, right? So this is going to give me 1/2 du over the square root of 1 plus x squared is the square root of u. And of course the reciprocal of the square root is just a negative 1/2 power. And this 1/2 constant I can pull outside. That would give me the integral of y to the negative third dy is equal to 1/2 integral u to the minus 1/2 du. Okay. To integrate both of those are simply power functions, so I can use the power rule for integration, which again, that means that I'm going to increase the exponent by 1 and then divide the antiderivative by the increased exponent. Y to the negative third, that means I will have y to the negative 2 and then divided by negative 2. And then on the other side, I will have, of course, the constant 1/2. Add 1 to the exponent. That means I would have u to the positive 1/2, but then divided by 1/2. And also, don't forget your constant of integration. Let's clean that up a little bit. We can see that the 1/2 factor and then divided by 1/2, those are going to cancel. So that is going to cancel with that. And then I can rewrite y to the negative 2 as the reciprocal of y squared. That would give me negative 1 over 2y squared. On the other side, again, the 1/2s cancel, leaving the square root of u. Remember that u was actually 1 plus x squared. This gives me the square root of 1 plus x squared plus c. Okay? As it sits, I have an implicit solution. I do not have y solved for, although, of course, using some algebra, we could very simply solve for it, which we will do. Now, before we continue further to get the actual explicit solution to this differential equation, let's see if we can solve for this constant c. If I go back to the original statement of the problem here, we had y of 0 equals negative 1. That means when x is 0, y would be negative 1. So within this differential equation, I'm going to substitute x is equal to 0, y is equal to negative 1, and then we will find out what the value of c would be. Let's go ahead and do that. When I plug in negative 1 for y, that would have negative 1 over 2 times negative 1 squared. Is equal to, on the other side, I would have the square root of 1 plus 0 squared plus c. All right, let's go ahead and simplify. Of course, the square of negative 1 is 1. 2 times 1 is 2, so this gives me negative 1/2 on the left-hand side. On the right-hand side, 0 squared is 0, 1 plus 0 is 1, square root of 1 is 1. That gives me 1 plus c, and then therefore c, by subtracting 1 to the other side, is negative 3 halves. So that would be the value of c in this particular case. Okay. Now what I'm going to do is let's take this explicit solution that we have here. Let's go ahead and start on the other side. We'll plug in the c value, and then we will find the explicit solution. Taking this equation, we have, or this equation right here, negative 1 over 2y squared is equal to the square root of 1 plus x squared minus 3 halves. This equation right here satisfies the initial condition. When x is 0 and y is negative 1, c is negative 3 halves. Again, that satisfies the initial condition. Let's go ahead and solve this. Well, what I could do is I could multiply both sides by 2y squared. But then I could also divide by this expression that I have on the right. So that'd be the square root of 1 plus x squared minus 3 halves. Divide that to both sides. Over on the left, I would get negative 1 over the square root of 1 plus x squared minus 3 halves is equal to 2y squared. Okay. And let's see, so then if I divide both sides by 2, or equivalently multiply by a half, I would get 2 square root 1 plus x squared minus 3 halves underneath negative 1 is equal to y squared. I can distribute that 2 through the parentheses, giving me negative 1 over 2 square root of 1 plus x squared minus 3 is equal to y squared. And then finally, just undo the square by using the square root. That would give me y is equal to plus or minus the square root of negative 1 over 2 square root 1 plus x squared minus 3. And using the initial condition, remember if y of 0 is negative 1, so let me put that back up here again just as a reminder, if y of 0 was negative 1. Okay, so let's go ahead and check that out. What that's going to tell me is, do I have the plus or the minus of the square root, because this is actually two different functions. If I plug in 0, I would have in the denominator 1 plus 0 squared, which is 1. The square root of 1 is 1. 2 times 1 is 2. 2 minus 3 would be negative 1. Negative 1 over negative 1 is positive 1. So therefore I need a negative out front. And that tells me that my explicit solution to the original differential equation is y is equal to negative square root of that expression. Okay. Again, the idea between for a separable differential equation is that I can write the original expression. I've got the derivative is equal to a combination of x's and y's, and I can write that combination of x and y's in a product with x's and y's. I can take the y stuff, to use the technical term there, divide it to the other side. I can integrate. Once I integrate, I can either solve for y to get an explicit solution or leave it as is to get an implicit solution. Thank you for watching, and please consider subscribing.